As stated earlier, we're going to use a graphing calculator to analyze graphs, particularly graphs that model real-life situations. Here's one of them. The total number of certified pilots in the United States is approximated by f of x equals 0.0000903x to the fourth minus 0.0166x to the third plus 0.762x squared plus 6.317x plus 7.708, where x is the number of years after 1930 and f of x is the number of pilots in thousands. Graph the function and describe its key features over the relevant domain. So first off, yes, we have a very complicated looking function here because the real world does not operate on just whole numbers. It has lots of decimals in this one. But it does ask for key features over the relevant domain. So let's talk about that for a second. Relevant domain and range. These are the values of the domain and range that fit the context of the real world problem. Because a lot of times these functions will create graphs, but only a portion of the graph makes sense in the context of the real world. We've talked about this before. For example, we know we can't have negative time. So anytime we have negative time, that the function models a negative time, we know that's not possible, so we should ignore that part of the graph or ignore answers that are generated that would be negative time. So the first thing we're going to do is we do need to graph this, so let's go to Desmos and graph that. When I first graph this, it looks very much like a parabola. The thing is that I know it's probably not a parabola because it has an x to the fourth power in it. And x to the fourth powers are going to have a few more twists and turns than just the single term that a parabola does. So what I really need to do is I need to zoom out. Let me zoom out of this. And as I zoom out, you can see that at a certain point, it does turn again. You can see there it goes up to this point right there, and then it turns back downward, and then to this point, and then it goes back upward again. And that should be the last place it turns. If I do zoom up and go further up, it doesn't look like it's going to turn anymore. And honestly, I know it's not going to turn anymore because I've already seen 3 turns here. And what you'll learn at a later date is that the number of turns are usually the degree minus 1. That's at least the maximum number of turns, but that's for a later time. But we also know, since it is an even degree, that it is going to increase forever, both left and right. So this is definitely the entire graph of this function. So let's start answering a few questions. So I will be switching back and forth between the graph and this page here. First off, the domain, well, that's an easy one because it is polynomial. The domain is all real numbers. The range, we're going to have to go back to the graph to see the range. So as I zoom into this graph, you can see that it does have a low point. The low point is right there at about negative 4.37548, and the graph doesn't go any lower than that, so the range is going to be y is greater than or equal to negative 4.37548. When we get to relative domain and the relative range, that's when things get interesting. So with the relative domain, it's the values of the domain and range that fit the context of the real world problem. So what does x represent in this problem? X is the number of years after 1930. That means x is a time. We are not going to go backwards in time. So we need to go to the graph and see where So since we can't go backwards in time, the absolute lowest value of x is going to be x is greater than or equal to 0, and that is going to be the relative domain. The relative range is going to be based upon the relative domain. Since the relative domain is x is greater than or equal to 0, the only quadrants that we're going to be dealing with is going to be quadrant 1. We're not going to be dealing with quadrant 4 either, because in quadrant 4, that would be where the y values are negative, and f of x is the number of pilots in thousands, which means we can't have negative number of pilots. So we're only going to be dealing with quadrant 1 when we analyze the rest of this graph. So as I go back to the graph, and I'm going to zoom out here, and here's what I'm going to do. I'm going to zoom out as far as I can. Well, not that far. And what I'm going to do is I'm going to take a picture starting with, there is the x value of 0 and everything else is to the right of that graph. And then I'm going to highlight some of the important points on the graph, particularly extrema. And we're going to answer based upon that picture right there. Okay, so our relative range. So this is only quadrant 1. The absolute lowest value in quadrant 1 that this graph achieves is right here, that 7.708. So the relative range is going to be y, or f of x, is greater than or equal to 7.708. And then we have extrema. Remember, extrema are the hills and the valleys, the high point and the low point. Again, we're only going to be dealing with extrema in the relative domain, in this case meaning quadrant 1. So the relative minimum in the relative domain, there is one valley in the relative domain, and it is right there at 87.16845, 566.96543. So I'm going to go ahead and round that as an ordered pair. So that would be about 87.17, 566.97. So that is the relative minimum of the relative in the relevant domain. That's a mouthful, I know. Then the relative maximum is going to be this point up here. And the relative maximum is about 54.39. That is the x value. But the y value, the relative maximum, 724.80 if I round to the nearest hundredth. In behavior in the relative domain. Now, again, so we're only dealing with quadrant 1. That means there's actually only one in behavior, and that is it is going to increase forever to the right. It's going to go that direction. So we're going to just say increase right, but that is it. We're actually not going to talk about the relative or the in behavior to the left, and the reason for that is because the graph abruptly stops right here in quadrant 1 and doesn't go any further. So there is no in behavior that's going to go decreasing forever that direction, because the graph has to stop there, because going into negatives will not make any sense. Intercepts in the relative domain, there is actually only one intercept in the relative domain, and it is a y-intercept. There is a y-intercept at 7.708. And symmetry in the relative domain, can you fold that in half? And I don't believe we can, so there is no symmetry. So most of the time, the relative domain is going to be dealing with just quadrant 1, because that's where all the values are positive. Let's try one more similar to that. This time we have coins. The number of quarters produced by the United States Mint can be approximated by the function f of x equals 16.4x to the third minus 149.5x squared minus 148.9x plus 3,215.4, where x is the number of years since 2005 and f of x is the total number of quarters produced in millions. Use a graph of the function to complete the table and describe its key features. So again, we'll go back to Desmos and we will graph that. When I first graph it, this is all I see. It just looks like a straight vertical line. Thing is I know it can't be just a straight vertical line, because it is a polynomial function and it is an x to the third power, which means it's going to be a curve somewhere. That just simply means we've not seen the entire graph. We're probably zoomed in too close. So let's zoom out. And as I zoom out, and I will tell you, I'm going to have to zoom out a long way. You can see that there is a curve happening way, way, way up there, because I can see that there is some sort of low point right there. And if I keep zooming out, and it's hard to tell because the graph kind of all runs into each other, So I'm going to make it, spread it out a little bit where I can see the graphs. You can see I'm spreading the x-axis out. And when I spread the x-axis out so that I'm actually going only by 20s on the x-axis, but I'm going by 2000s on the y-axis, you can see that it is definitely a curve. It's just a very tall, long, skinny curve. So that is going to give me the relative information that I need to start answering some questions. First off, the domain. The domain of a polynomial function is all real numbers. And the range. The range of this particular function, let me go back to it. You can see that the range is going to be decreasing to the left but increasing to the right, and when a graph does that, it means that the range is also all real numbers. And then we get to the relative domain. Relevant domain means it's going to be just numbers that have x values that are positive, and I know this because it says x is the number of years since 2005. Look at that, we're dealing with another time again. So the relative domain is going to be x has to be greater than or equal to 0. The relative range means that we're only dealing with quadrant 1 again. So as I go back to the graph, I'm only going to focus on quadrant 1. So let me zoom in on quadrant 1 and take a picture like I did on the previous graph. And in the process, I do need to highlight some important points. So if we're only dealing with quadrant 1, the relative range is going to be starting from this point down here. That is the lowest point in the relative range. And so the y value of that point is about 434.75. So the relative range will be y has to be greater than or equal to 434.75. Extrema. We do have a relative minimum down there at that exact same point. So there is a relative minimum at the ordered pair. Approximately 6.54 is the x value of that. And the y value again is at 434.75 estimated. The relative maximum of the relative domain. This is where it can get a little tricky because you can see, if I zoom in, that there is a maximum right here on this point, and this is the value of the maximum. The problem is that point is actually not part of the relative domain because of this value right there. The x value is a negative value, and that means it's not in quadrant 1. Quadrant 1 only has positive numbers. So even though that is a high point on the graph as a whole, it is not a high point in the relative domain because that does not make sense because the x value would represent negative time. And as we've said so many times before, we can't have negative time. So in the relative domain, there is no relative maximum. In behavior in the relative domain, it does increase forever to the right, so it is going to increase right. But it isn't going to do nothing to the left because we can't go farther than this 3,215.4 because that's where the graph starts. So there is no, does not have any domain. So it does not have any in behavior to the left. Intercepts in the relative domain, there is one intercept in the relative domain, and it is where the graph starts, where the x value is 0. It does have a y value of 3,215.4, so there is a y-intercept right there. But does not have an x-intercept in the relative domain because the only x-intercept was when it was going down that way into quadrant number 2 where the x values are negative. Symmetry in the relative domain, can't quite fold it in half on this one either, so there is no symmetry.